there's one other thing we want to talk about with vectors, and that would be vector components. Now what we've done is we've started with two legs, we've added those two legs together to find the resultant. But sometimes we start with the resultant and we want to know what the two legs were. The two legs are the components, the pieces that went into building the vector. And I'm going to draw a few lines on here. Okay, so we have just a bunch of random diagonal lines. Now each one of these diagonal lines represents a vector quantity. That vector quantity would have what two things? Magnitude and direction. Exactly. So magnitude and direction. If I start with this one, we'll call it vector A. Vector A could be the resultant of two pieces or two legs. I'm just going to draw those two legs in. Then we'll talk about what they mean in a moment. What we're basically doing is the opposite of what we did before. So if A is our vector, then we have two legs that made up that vector. We would have an x component and a y component. So if this is A, this would be A sub x, and this would be A sub y. And this would be some angle theta we're going to come back to. We do the same thing with the rest of these vectors. And it doesn't matter which side you draw them on, as long as you remember to hold true to the head to tail. I'm going to draw these in and then we'll label them. Alright, so if this is B, this would be the x component. That would be our y component. If this was C, x component, y component. Maybe this is D, x component, and a really, really small y component. So why is this such a big deal? Oh, don't forget our angles. What we need to be able to do is we need to be able to figure out what our x and y components are. So I'm going to start with A. We're going to figure out what A sub y is and A sub x actually are. So if we have A, let's say A is some vector and we'll give it some numbers. We'll say that it is 32.4 meters, and the direction would be, if this was our direction, 47 degrees north of the east line. Okay, so that is our vector. 32.4 meters, that's a 4, 47 degrees north of east. We need to find the x component and the y component that would have created such a vector. Remember, we have SOHCAHTOA. SOHCAHTOA is your best friend. So in order to find out A sub x, we're going to have to use, in this particular instance, we are kind of locked into what we use, because we have the hypotenuse, we have the angle, and we're looking for one of the two sides. In this particular instance, we're looking for the side that is adjacent to the angle. If it's adjacent to the angle, if you remember your SOHCAHTOA, your trig identities, that means we must use cosine. So AX, if we just write down the cosine of theta, we would say the cosine of theta is equal to the opposite side, which is AX, over the hypotenuse, which is A, or which is just plain A. So if I'm looking for A sub x and I solve this for A sub x, then I would write A sub x is equal to A times the cosine of theta. Well, we said A was 32.4 meters and we said that theta was 47 degrees. So we do 32.4 times the cosine of 47. And when we put that in the calculator, I do not second cosine, but actually cosine of 47, close that off, times 32.4, and I get that that is 22.1 meters. So AX is 22.1 meters. Now I need to find AY. So if I want to find AY is, if you look at our picture, That is opposite of theta, so we're going to use sine. So it's going to be sine of theta is equal to the opposite, which is a sub y, over the hypotenuse, which is a. I'm looking for a sub y, so I'm going to solve for a sub y. A sub y is equal to a times the sine of theta. Now put my numbers in. A is 32.4 meters times the sine of 47 degrees. .4 times the sine 47, and I get 23.7 meters. So what I'm saying is that on the x component it would be 22.1 meters east. On the y component it would be 23.7 meters north. If we took 22.1 meters east and added that to 23.7 meters north, then our resultant would be 32.4 meters, 47 degrees north of east. If we wanted to do that one more time just to make sure that that's cemented, let's do B. If I redraw B, looks something like this. And yes, I'm being bad, I'm not using the straight edge. This is Bx, this would be B sub y. This would be theta. So B has a magnitude of 17.2 meters per second and a direction 37.4 degrees south of west. What would be Bx and what is By? Alright, if I start with Bx, Bx again is forming an adjacent, so I'm going to use cosine. And if I write down the cosine of theta is going to equal the adjacent, which is Bx, over the hypotenuse, which is B. So Bx then equals B times the cosine of theta. Well, we said B was 17.2, and we said that theta is 37.4 degrees. And we said that beta was 37.4 degrees, so we need the cosine of 37.4 degrees. Okay, plug this into the calculator. 17.2 times the cosine 37.4, and that gives us 13.7 meters per second. Now which direction is it going? It's going to the west. 13.7 meters per second to the west. By then centers around the sine of the angle, because it would be opposite my angle. So this time I would say sine of theta equals By over B. So if I solve for By, B sine theta, I feel like I'm playing bingo. B is 17.2 meters per second. And then we take the sine of 37.4 degrees, and we would get 17.2 times the sine of 37.4. 10.4 meters per second. What direction? South. So in order to get a resultant vector of 17.2 meters per second that is 37.4 degrees south of west, we would need to have 13.7 meters per second west. At the same time we have 10.4 meters per second south. These two are the components of that. And there you have it.